In July 2022, a machine parked a million miles from Earth opened its eyes for the first time. It had taken 25 years to build. It cost $10 billion. It nearly failed twice during assembly, once during launch, and once during the 6-month unfolding sequence that had 344 single points of failure. Any one of them would have turned the most expensive scientific instrument in human history into a piece of drifting metal, but it did not fail. The James Webb Space Telescope reached a point in space where the Sun, the Earth, and the Moon are always behind it. It cooled down to 40 degrees above absolute zero. It pointed its gold-plated mirror at a tiny patch of sky, a patch the size of a grain of sand held at the end of your outstretched arm. 12.5 hours of exposure. And when the first image came back, the teams at the Space Telescope Science Institute went quiet. Not because the picture was beautiful, it was. Not because the resolution was impressive. It was the sharpest deep field image ever taken. They went quiet because the objects in the image should not exist. There were galaxies in that tiny patch of sky that were too old, too massive, and too organized for the age of the universe at that distance. The telescope was working perfectly, better than specification. The instruments were more sensitive than the engineering teams had promised. The optics were sharper than anyone had a right to expect. Every component of the machine was doing exactly what it was designed to do. The problem was not the machine. The problem was that the universe did not match the blueprints we had drawn for it. Every major dataset since that first image has carried the same message. Your models are off. Your timelines do not work. The things you thought you understood less than you believed. And every correction that followed did not make the picture clearer. It made the picture more precise, more hostile, and more difficult to explain without asking questions that none of our current physics can answer. To understand what this telescope actually does, you have to understand what Hubble could not do. Hubble sees visible light, the same wavelengths your eyes detect. Blues, whites, reds. If a star is bright enough and close enough, Hubble can photograph it in extraordinary detail. But the universe has a problem that visible light cannot solve. Objects that are extremely far away are also extremely old. Their light has been traveling for billions of years, and during those billions of years, something has been happening to that light. Space has been expanding, not the objects flying apart through space. Space itself, the distance between things, has been growing the entire time the light was in transit. When space stretches, it stretches the wavelength of the light, traveling through it. Short wavelengths get pulled longer. Blue light turns red. Red light turns infrared. And infrared is heat radiation. Your eyes cannot detect it. Hubble cannot detect it. The oldest and most distant objects in the universe have had their light stretched so far that they are completely invisible to every optical telescope ever built. They are there. They are radiating. But they are radiating in a frequency that no one was listening to. JWST listens to that frequency. Its mirror is coated in gold, 48 nanometers thick, roughly 1,000 times thinner than a strand of your hair. Gold was chosen because it reflects infrared light more efficiently than any other metal. The mirror itself is 6.5 meters across, made of 18 hexagonal segments cut from beryllium, a metal that holds its shape when it gets extremely cold, and it has to be cold. JWST operates behind a thermal shield the size of a tennis court, 5 layers of a material called capton, each thinner than a human hair. On the side facing the sun, the shield heats to 85 degrees Celsius. On the mirror side, it drops to negative 233. That gap, over 300 degrees of difference, is what separates the telescope from noise. It sits in permanent shadow, in permanent cold, with nothing between its mirror and the oldest light in the universe. Hubble gave us a brilliant view of the neighborhood. JWST showed us that the neighborhood has a basement we never knew was there. And the basement goes down further than the building goes up. The teams running the telescope expected to confirm what they already knew. The theoretical models were specific about what the early universe should look like. The first few 100 million years after the Big Bang should be sparse, dark, quiet. Small clumps of hydrogen gas slowly collapsing under their own gravity, forming the first dim proto-galaxies over hundreds of millions of years. Simple structures, faint signals, that was the prediction. The data came back and it did not match. The first deep field images were not sparse, they were packed. Galaxies everywhere, not at the edge of detection, not faint smears that needed months of processing to resolve, but bright, structured objects with defined shapes and measurable masses. And they were not young. They were already finished, already organized, already old in a way that should have taken billions of years to achieve, sitting in a part of the timeline where billions of years had not yet passed. Jane Rigby is the operations project scientist for JWST. She is the person responsible for making sure the telescope does what it was built to do. And by every engineering metric, it was doing more than that. The optics were sharper than the design required. The sensitivity was higher than anyone had modeled. The pointing accuracy was tighter than the specifications demanded. Rigby confirmed that the machine was exceeding its own blueprint, but she also confirmed something else. The universe was not matching the predictions. The telescope was seeing things that the models said should not be there. Marcia Rika, the principal investigator for NIRCam, the primary camera on board, reported the same pattern. Too many sources at high redshift. Too bright. Too early. There is a very specific kind of problem in science where the instrument works perfectly and the data still contradicts the theory. It means the error is not in your equipment. It is in your understanding. When the lens is clean and the picture still looks wrong, the problem is not the lens. The problem is what you are looking at. Redshift 13. In astronomy, redshift measures how much the expansion of space has stretched the light traveling through it. The higher the number, the older the light, and the further back in time you are looking. Redshift 13 means the light you are seeing left its source, roughly 13.5 billion years ago, when the universe was about 300 million years old. The universe right now is 13.8 billion years old. So 300 million years is about 2% of its current age. If the entire history of the universe were a single year, redshift 13 is January 1st, somewhere around 7 in the morning. And what JWST found at 7 in the morning was not what anyone predicted. Glass-C13 was among the first objects identified in the early JWST data, a galaxy candidate at a redshift that should have been empty. Then came JADES-GS-Z14-0, confirmed spectroscopically in 2024, pushing past redshift 14 to roughly 290 million years after the Big Bang. These are not smudges at the edge of detection. They are structured. They have mass. They contain stars that have already lived, fused hydrogen into helium, produced heavier elements, scattered those elements into the surrounding gas, and seeded the next generation of stars. That cycle, the birth and death of a stellar generation, takes hundreds of millions of years at minimum. But these galaxies are already showing the chemical signatures of completed cycles at an age when, according to every model we had, the first stars should barely have begun to ignite. Think of it this way. You walk onto a construction site. The foundation was poured yesterday morning. The concrete is still dark and damp. The rebar is still visible. And standing in the middle of the lot is a finished 40-story building. Not a frame, not a skeleton. A finished building with glass in the windows, lights on in the offices, and people inside working at desks. You did not miss the construction. There was not enough time for construction. The building has no business being there. But it is there. And it is not empty or broken. It is running. Something assembled it in a way that your blueprints say is not possible. That is what is sitting at redshift 13. Fully formed galaxies with no time to have formed. And the data is not ambiguous. The spectroscopy confirmed it. The photometry confirmed it. The mass estimates held up under peer review. The objects are real. The timeline is real. And the two do not fit together. In February 2023, a paper landed in Nature that made the problem worse. A team led by Ivo Labbé, an astronomer at Swinburne University of Technology in Australia, reported 6 galaxies from the first 500 to 700 million years of the universe. That alone would have been notable, but the masses were the problem. These were not small, faint, early galaxies struggling to pull themselves together. These were massive. Some of them weighed as much as the Milky Way. Our galaxy, the one you are sitting in right now, is 13 billion years old. It took that entire span to accumulate its 100 billion stars, to build its spiral arms, to grow its central supermassive black hole to 4 million solar masses. These 6 objects had achieved comparable mass when the universe was 3% of its current age. 3%. If you took the lifetime of the universe and turned it into a 100-meter sprint, these galaxies had already crossed the finish line while the starting gun was still echoing off the bleachers. Labbé called them universe breakers, not as a joke, as a description. They break the standard cosmological model known as lambda CDM. Lambda CDM is the best model we have. It has been tested for decades. It describes the expansion of the universe, the distribution of galaxies, the behavior of dark matter, the cosmic microwave background. It works extraordinarily well at large scales. But lambda CDM is also very specific about how fast galaxies can grow. There is a budget. Matter can only collapse so quickly under gravity. Gas can only cool and condense into stars at a certain rate. Feedback from young stars blows surrounding material away, slowing the process further. The model sets a speed limit on galaxy assembly, and these 6 objects were doing 80 in a school zone. The immediate question was whether the data was real. Early photometric estimates can be wrong. A galaxy might look massive at first glance because its light is being contaminated by something else. An active nucleus, a foreground star, a calibration artifact. But follow-up observations with NIR SPEC, the spectroscopic instrument on JWST, confirmed the redshifts for several of the candidates. The distances held. The masses were revised downward slightly in some cases, but not enough. The objects are lighter than the first estimate, but they are still far too heavy for the time they had. The data is cleaner now, and the problem did not go away. It got sharper. To see why this is so damaging, you have to understand the blueprint that lambda CDM uses for galaxy assembly. The model is called hierarchical merging. It was formalized by Simon White and Martin Rees in 1978, and it has been the backbone of our understanding of structure formation ever since. The idea is simple and elegant. After the Big Bang, the universe was filled with a nearly uniform cloud of gas and dark matter. Nearly uniform, but not perfectly. There were tiny density fluctuations, regions where the matter was packed slightly tighter than the average. Gravity amplified those fluctuations. Denser regions pulled in more material. Over hundreds of millions of years, those regions collapsed into small halos of dark matter surrounded by gas. The gas cooled, fell to the center, and formed the first stars. These small halos then merged with each other. 2 small halos crash together and form a medium halo. Medium halos merge and form large ones. Large ones collide and form galaxy clusters. It is construction from the bottom up. Bricks before walls, walls before floors, floors before buildings. The process is slow because each step has to finish before the next one can start. You cannot build the second floor until the first floor can hold the weight. And the model has been tested against simulations thousands of times. It matches the distribution of galaxies we observe in the nearby universe. It matches the filamentary structure of the cosmic web. It matches the clustering patterns at medium redshifts. It works. But what JWST found at redshift 13 is the equivalent of walking onto a construction site where the bricks have not been delivered yet, and finding the building already standing. The small halos that should have served as bricks had not had time to form. The merging sequence that should have built these galaxies step by step had not had time to run. Yet the building is there, fully assembled with the lights on. Hierarchical merging does not explain this. It cannot. The speed limit of the model is not a suggestion. It is derived from the physics of gravitational collapse, from the cooling rate of hydrogen, from the feedback pressure of young stars. These are not parameters you can fudge without breaking the other predictions that depend on them. If you raise the speed limit in the early universe, you ruin the fit at later times. The model is consistent precisely because it is constrained, and JWST just showed us that the early universe did not obey the constraint. So if the standard assembly line does not work, what does? There are 3 hypotheses on the table right now, and none of them are comfortable. The first is direct collapse. Volker Brom at the University of Texas and Abraham Loeb at Harvard have been developing this idea for years. The standard pathway to a black hole goes through a star. A massive star burns through its fuel, collapses, explodes, and leaves behind a stellar mass black hole, maybe 5 to 50 times the mass of the Sun. That black hole then grows by feeding on gas, slowly, over billions of years. But what if the first black holes did not need a star? What if, in the conditions of the very early universe, massive clouds of pristine hydrogen gas collapsed directly into black holes without ever forming a star in between? No fusion, no supernova, no stellar remnant, just gravity pulling a cloud past the point of no return. These direct collapse black holes could have been born with masses of 10,000 to 100,000 suns. And once you have a seed that heavy, it does not need billions of years to grow into a monster. It has a head start. It pulls in gas fast enough to build a galaxy around itself in a few 100 million years. The problem with this solution is that it requires very specific conditions. The gas cloud has to be massive, pristine, and free of the molecular hydrogen that would normally cause it to fragment into smaller clumps and form stars instead of one giant collapse. You need a very particular environment in the early universe to make this work. The second hypothesis attacks dark matter itself. The standard model uses cold dark matter, particles that move slowly and clump efficiently. But what if dark matter in the early universe was warm or fuzzy? Lighter particles with longer wavelengths that behave differently at small scales. Warm dark matter suppresses the formation of small halos, but allows larger structures to form more quickly under certain conditions. This would change the bottom-up assembly sequence entirely, but the cost is high. Cold dark matter matches the cosmic microwave background data with extraordinary precision. If you swap it out, you have to explain why the CMB still looks the way it does. The third hypothesis is the most unsettling. It suggests that the initial conditions of the Big Bang itself were different from what we assumed. The density fluctuations that seeded the first structures may have been stronger or distributed differently, or amplified by a mechanism we have not identified. If that is the case, the problem is not with any single component of the model. The problem is with the starting point. We wrote the first page of the story wrong, and everything we built on top of it inherited the error. Each of these 3 doors leads somewhere uncomfortable. Door 1 rewrites how black holes form. Door 2 rewrites what dark matter is. Door 3 rewrites the Big Bang. There is no door marked minor adjustment. Every path leads to a rebuild. If the initial conditions of the Big Bang might be wrong, then everything that flows from those conditions has to be rechecked. And there is one measurement that flows from everything: the rate at which the universe is expanding. It is called the Hubble constant, labeled h0, and it is supposed to be a single number. One value. The speed at which galaxies are moving apart from each other per unit of distance. Measure it, and you know how fast the universe is growing. Measure it accurately, and you can calculate the age of the universe, its geometry, and its fate. The problem is that we have 2 ways to measure it, and they disagree. The first method looks at objects near us. Adam Rees, a physicist at Johns Hopkins who shared the Nobel Prize in 2011 for the discovery that the expansion of the universe is accelerating, leads a project called SHOES. The method works like this. You start with a type of star called a Cepheid variable. Cepheids pulse. They brighten and dim in a regular rhythm, and the speed of that rhythm is directly related to how bright the star actually is. If you know how bright a star really is, and you measure how bright it looks from here, the difference tells you how far away it is. You calibrate Cepheids in nearby galaxies. Then you use those calibrated Cepheids to measure the distances to galaxies that contain a specific type of supernova, called Type 1a. Type 1a supernova all explode with roughly the same brightness. They are the gold standard of cosmic distance measurement. You use them to reach further out, measure the recession speed of those galaxies, and divide by the distance. That gives you h0. Reese gets 73 kilometers per second per megaparsec. The second method does not look at nearby objects at all. It looks at the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang. The Planck satellite, operated by the European Space Agency, mapped this afterglow with extraordinary precision in 2018. From the patterns in that map, the tiny temperature fluctuations imprinted when the universe was 380,000 years old, you can calculate what the expansion rate should be today, assuming the standard cosmological model is correct. Planck gets 67.4, 73 versus 67, 6 units apart. For years, physicists assumed this was a measurement error. Somebody's calibration was off. Somebody's data had a systematic bias they had not found yet. But both teams checked their work. Both teams improved their instruments. Both teams published paper after paper, tightening their error bars. And the gap did not close. It widened. This is not two amateurs getting different answers on a homework problem. This is two of the most precise measurement programs in the history of physics, using completely independent methods, pointing at completely different parts of the universe, and arriving at numbers that cannot both be right. JWST was supposed to fix this. That was one of the promises. The Hubble tension, as physicists started calling it, had been nagging the field for over a decade, and the leading suspect was calibration. The Cepheid distance ladder, the chain of measurements that Reese used to get his number, depends on knowing exactly how far away the calibrating galaxies are. If that anchor is off by even a small amount, the error propagates through every rung of the ladder. Hubble measured those Cepheids, but Hubble has limits. Its resolution in crowded star fields is not perfect. If two stars sit too close together, their light blends into a single point, and you overestimate the brightness. Overestimate the brightness, you underestimate the distance. Underestimate the distance, you get a higher expansion rate. That was the hope. JWST resolves individual stars far better than Hubble. If the blending was the problem, JWST would separate the stars, correct the brightness, and the number would shift downward. Tension solved. Wendy Friedman, an astronomer at the University of Chicago, ran exactly this test. She leads a project called the Chicago Carnegie Hubble Program, and she has spent her career building an independent distance ladder using a different kind of star, the tip of the red giant branch. Red giants are old stars that have exhausted the hydrogen in their cores. As they age, they climb a predictable track in brightness until they hit a ceiling. A maximum luminosity that is remarkably consistent across different galaxies. That ceiling gives you a distance anchor that does not depend on Cepheids at all. Friedman pointed JWST at galaxies where both Cepheids and red giant branch stars are visible. She measured both. Her red giant branch distances came in closer to the Planck number, lower expansion rate, tension easing, but Reese reanalyzed the same JWST data using his Cepheid method, and got a number that was still high, still 73. The same telescope, the same photons, two different methods, two different answers, and the distance between those answers did not collapse. The tension did not dissolve. It calcified. Here is what that means. If the problem were a telescope artifact, JWST would have erased it. It did not. If the problem were a calibration error in one method, the other method would have overruled it. It did not. The two methods still disagree, and now they disagree using the sharpest data in history. This is not a problem you can solve by building a better ruler. The ruler is fine. The thing you are measuring does not behave the way your equations say it should. If two independent methods of measuring the same thing give you different answers, and neither method is wrong, then your understanding of the thing itself is incomplete. Something is missing from the equation. And in cosmology, there is one equation that governs everything. It was written in 1922 by Alexander Friedmann, a Russian physicist who died of typhoid at the age of 37, 2 years after publishing the paper that would define the next century of cosmology. The Friedmann equation is deceptively simple. On one side, you put the expansion rate. On the other side, you put everything that is in the universe, matter, radiation, and whatever is causing the expansion to accelerate. The equation says these two sides must balance. The expansion rate is determined by the contents. If you know what the universe is made of, you know how fast it is growing. If you know how fast it is growing, you can work backward and figure out what it is made of. But here's the problem. The two sides are not balancing. The contents we measure from the early universe using the cosmic microwave background predict an expansion rate of 67. The expansion rate we measure directly using nearby stars and supernovae gives us 73. That 6-unit gap means one of two things. Either we are measuring the contents wrong, meaning there is more matter or energy in the universe than we have accounted for, something hiding in the ledger that we have not found, or the equation itself is incomplete, meaning the relationship between contents and expansion is not as simple as Friedmann wrote it. Think of it like a household budget. You know your income, you know your expenses, you subtract one from the other, and the result should be your bank balance. But every month, the balance is off by the same amount. It is not random, it is consistent. Either you have an expense you forgot to write down, a subscription you do not remember signing up for, or the bank is applying a rule you do not know about. In cosmology, the forgotten subscription might be a new form of energy, something that was active in the early universe and has since faded. The unknown bank rule might be a modification to gravity itself, a behavior that Einstein did not account for. Either way, the budget does not close. And a budget that does not close means you do not understand your own finances. At the scale of the universe, not understanding your own finances means you do not know what reality is made of. One of the candidates for the missing line in the budget is an idea called early dark energy. It was proposed by Tanvi Karwal and Mark Kamiankowski at Johns Hopkins in 2016, and it has been refined by Vivian Poulin and collaborators since 2019. The standard model treats dark energy as a constant. It is the same everywhere. It does not change over time. It pushes the expansion at a fixed rate, and it has been doing so for billions of years. That constancy is baked into the cosmological constant, the lambda in lambda CDM, the same lambda that is tuned to 10 to the negative 120. But what if lambda was not always constant? What if, in the first few 100,000 years of the universe, there was an additional burst of dark energy, a spike that pushed the expansion faster than the standard model predicts, and then faded away before the universe was 1 million years old? If that spike existed, it would change the sound horizon, the scale of the ripples in the cosmic microwave background. The sound horizon is the ruler that Planck uses to calculate h0. If the ruler was shorter than Planck assumes, the calculated expansion rate comes out higher, closer to 73. The tension eases, the math is clean, the models fit, but the implication is heavy. If dark energy is not a constant, then the force that controls the fate of the universe is not fixed. It has changed before, and if it has changed before, it can change again. You are living inside a machine that does not run at one speed. It shifts. It has gears, and you do not have access to the gearbox. You do not know how many gears there are. You do not know what triggers the shift. You do not know if the current gear is the last one, or if there is another shift coming that will change the expansion rate in a direction we cannot predict. The universe might slow down, it might speed up, it might reverse. We do not know because we do not understand the mechanism. We named it dark energy and we gave it a Greek letter, and we treated it like a fixed property of space. But JWST and the Hubble tension are telling us that it might not be fixed at all. And if the force that determines whether the universe expands forever or tears itself apart is a variable, not a constant, then we do not know the ending of this story. We assumed we did. We were wrong. If the force that drives expansion might be a variable, the question becomes, what else in the universe do we not understand? And the honest answer is, most of it, 95% of it. To see why, we need to look at what JWST has been doing with light that bends. When light from a distant galaxy passes near something massive, a galaxy cluster, a concentration of matter, gravity bends the light. Not a little. Visibly. The distant galaxy gets stretched into an arc, sometimes smeared into a ring, sometimes split into multiple copies appearing at different positions around the cluster. This is gravitational lensing, and Einstein predicted it in 1915. But JWST turned it into a diagnostic tool. The amount of bending tells you how much mass is doing the bending. And when the teams mapped the bending around clusters like SMA CS0723, Able 2744, the cluster astronomers call Pandora, and El Gordo, the most massive galaxy cluster known at high redshift, they found a consistent result. The visible matter, the galaxies, the gas, the stars, accounts for a fraction of the bending. Something else is providing the rest of the gravitational pull. Something that does not emit light, does not absorb light, does not interact with electromagnetic radiation at all. It is there because the math demands it. The arcs are too curved, the images too distorted, the geometry too warped to be explained by the matter you can see. This invisible mass is not a new discovery. Fritz Zwicky, a Swiss astronomer with a reputation for being abrasive and usually right, first noticed the discrepancy in 1933. He was studying the Coma cluster, a collection of over 1,000 galaxies about 320 million light-years away. He measured how fast the galaxies were moving within the cluster and calculated how much mass was needed to hold them together gravitationally. The visible mass was not even close. The galaxies were moving too fast. They should have flown apart long ago. Something unseen was holding them together. 40 years later, Vera Rubin, working at the Carnegie Institution, measured the rotation speeds of stars in individual galaxies. Stars at the outer edges were orbiting just as fast as stars near the center. That should not happen. In a system held together by visible mass alone, the outer stars should be moving slower, the same way Pluto orbits the Sun more slowly than Mercury. But the rotation curves were flat. The speeds did not drop off. The only explanation was a halo of invisible mass surrounding each galaxy, extending far beyond the visible disk. We named it dark matter. Naming it felt like progress, but naming is not understanding. JWST did something neither Zwicky nor Rubin could do. It mapped the shape. The lensing data does not just tell you that dark matter exists, it tells you where it is, and the maps show structure, not a smooth, uniform fog. Filaments, walls, knots, corridors of density connecting clusters across millions of light years, an architecture invisible to every telescope that sees in light, but real enough to bend the images of everything behind it. Dark matter is not a gap in our knowledge, it is the scaffolding of reality. And we cannot see it, touch it, catch it, or explain what it is made of. Dark matter is the skeleton. But skeletons do not move on their own. Something has to push. Something has to drive the expansion that stretches space, that pulls galaxies apart, that determines whether the universe keeps growing forever or eventually stalls. That something is dark energy. And in April 2024, a project called DESI, the Dark Energy Spectroscopic Instrument, released its first batch of results, and those results contained a crack. DESI is not a space telescope. It is a ground-based instrument mounted on a 4-meter telescope in Arizona, fitted with 5,000 tiny robotic fiber optic positioners that can simultaneously capture the spectra of 5,000 galaxies at once. Over its 5-year survey, it will map the 3-dimensional positions of roughly 40 million galaxies and quasars, building the most detailed map of the universe's expansion history ever attempted. The goal is to measure how the expansion rate has changed over time. Not just its value today, but its shape across billions of years. A curve, not a point. The standard model says that curves should be flat. Dark energy, represented by the cosmological constant lambda, is supposed to be the same everywhere and at all times. It does not evolve, it does not weaken, it does not strengthen, it just pushes, steadily, forever. That flatness is the foundation of every prediction about the future of the universe. If lambda is constant, the expansion accelerates forever. Galaxies drift apart, stars burn out. The universe ends in cold, empty silence. But the first year of DESI data hints that the curve is not flat. The team tested a model called W0 W sub A, which allows dark energy to change strength over time. And the data showed a mild preference for dark energy that was stronger in the past and is weakening now. Not a decisive result, not a 5 sigma detection, but a lean. A tilt in a direction that the standard model does not allow. If that tilt holds up with more data, the consequences are difficult to overstate. A changing dark energy means the future of the universe is not determined. The expansion might not accelerate forever. It might slow down. It might reverse. The ending we thought we had calculated, the cold death, the infinite dilution, might not be the ending at all. We treated lambda as a fact, a fixed property of space that we could set and forget. DESI is suggesting it might be a variable. And a variable that controls the fate of everything is a variable you want to understand. We do not. Take a step back. Look at the full inventory. Ordinary matter, the stuff that makes up stars, planets, your body, the screen you are looking at, every atom in every object you have ever touched, accounts for roughly 5% of the total energy content of the universe. 5%. Dark matter, the invisible scaffolding that bends light and holds galaxies together but does not interact with anything we can build a detector for, makes up about 27%. Dark energy, the force that drives the expansion and might or might not be changing strength as we speak, accounts for the remaining 68%. We built the entirety of physics on 5%. Every equation, every experiment, every theory of particles, fields, forces, chemistry, biology, all of it describes the behavior of the thin surface layer. The remaining 95% is a machine we labeled but did not open. We gave it names, we measured its effects, we inferred its presence from the motion of galaxies and the bending of light. But we do not know what dark matter is made of. We do not know what dark energy is. We do not know why they have the proportions they have. And JWST, combined with ground-based surveys, has confirmed that this 95% is not formless. It has architecture. The galaxies are not scattered at random across space. They are organized into filaments, long threads of matter stretching across hundreds of millions of light years, connected at nodes where galaxy clusters sit like knots in a net. Between the filaments are voids, enormous empty regions, some over 300 megaparsecs across, where almost nothing exists. The whole structure looks like a web, a cosmic web, and the web is not made of visible matter. The filaments are traced by galaxies, but the filaments themselves are dark matter. The galaxies are passengers. The dark matter is the road. JWST has found protoclusters at redshifts above 7, dense knots of galaxies forming along filaments in the first billion years. The web was already being woven when the universe was a fraction of its current age. The architecture was already there. We are not at the center of this web. We are not at a major node. We are on a filament, one thread among billions, surrounded by voids that are emptier than any vacuum we can produce on Earth. Our position in this structure is not special. It is not privileged. It is the cosmic equivalent of a house on a side road between two highways with nothing but empty fields in every direction for as far as you can see. And the highways are made of something you cannot identify. We are standing on 5% of reality, woven into an invisible web we did not build and cannot see. But this web had to start somewhere. Every filament, every knot, every void started as a fluctuation in the first moments after the Big Bang. And the very first objects to catch fire in that darkness were the stars we have never seen. Astronomers call them Population 3. The naming convention is backwards for historical reasons. Population 1 stars are young, metal-rich stars like the Sun. Population 2 are older, metal-poor, found in the halos and globular clusters of galaxies. Population 3 is the theoretical generation that came before either of them. The first stars, born from gas that had never been inside another star. Pure hydrogen, pure helium, and trace amounts of lithium. No carbon, no oxygen, no iron, no dust. Just the two lightest elements in the periodic table, collapsing under gravity in a universe that had no structure yet, no feedback, no magnetic fields worth mentioning. The models predict that these stars were massive. Without heavier elements to help the gas cool efficiently, the collapsing clouds could not fragment into small pieces the way they do today. Instead, they formed single enormous objects, stars with 50, 100, maybe 300 times the mass of the Sun. Furnaces so hot they burned through their fuel in a couple of million years, then died in violent explosions that seeded the surrounding gas with the first heavy elements, the first carbon, the first oxygen, the first building blocks of everything that would come later, including you. No one has ever directly observed a Population 3 star. They died billions of years ago, but JWST is looking for their fingerprints. In 2024, Roberto Maiolino and his team at Cambridge published results from GN-Z11, a galaxy at redshift 10.6, roughly 430 million years after the Big Bang. They found pockets of gas with extremely low metallicity, lower than anything previously measured at that distance. Not zero, not pristine, but close enough to suggest that the first generation of stars had only recently finished their work and scattered their ashes into the surrounding gas. The first campfires of the universe, and we are finding the warm coals. But even here, at the very beginning, something does not fit. The models predict that the first star should ignite slowly, in isolated pockets, separated by vast stretches of empty gas. What JWST is showing is that the ignition was faster, denser, and more widespread than the models allow. The first fires burned hotter and start sooner than we calculated. The anomaly is not confined to the galaxies that formed later. It reaches all the way back to the very first light. If the first stars ignited faster than they should have, something else was keeping pace. In 2023, a team led by Arkos Bogdan at the Harvard-Smithsonian Center for Astrophysics pointed two telescopes at the same patch of sky. JWST provided the infrared image. Chandra, NASA's X-ray observatory, provided the high-energy view. Behind the galaxy cluster Abell 2744, magnified by gravitational lensing, they found an object called UHZ1. It was faint, it was small, and it was screaming in X-rays. X-ray emission at that intensity, at that distance, means one thing. A supermassive black hole, not a stellar mass black hole, the kind that forms when a single large star collapses. A monster. Roughly 10 million times the mass of the Sun. And it existed 470 million years after the Big Bang. To understand why that is a problem, you need to understand how black holes are supposed to grow. The standard model starts with a dead star. A star 20 or 30 times the mass of the Sun runs out of fuel, its core collapses, and the result is a black hole weighing maybe 5 to 50 solar masses. That black hole then grows by pulling in gas from its surroundings. Gas spirals inward, forms a hot disk, and gradually feeds the black hole. But there is a speed limit on this feeding. It is called the Eddington limit. As gas falls toward a black hole, it heats up and radiates energy outward. That radiation pushes against the incoming gas. At a certain feeding rate, the outward push of radiation exactly balances the inward pull of gravity. The black hole cannot eat any faster. It is like trying to drink from a fire hose. The pressure of the water hitting your face prevents you from swallowing. If you start with a 50 solar mass seed and feed it at the maximum rate allowed by the Eddington limit, continuously, without interruption, for 470 million years, you get a black hole in the range of a few 100,000 solar masses. Maybe 1 million if you are generous with the assumptions. You do not get 10 million. The math does not work. The seed is too small, the time is too short, and the speed limit is too strict. So either UHZ1 ate faster than the Eddington limit allows, which would require conditions that are not well understood and not easy to sustain, or it did not start as a small seed. It started big. And that means something happened in the early universe that skipped the normal pathway entirely. Priyamvada Natarajan, a theoretical astrophysicist at Yale, has been working on this problem for over a decade. Her argument is straightforward. If the standard pathway cannot produce a 10 million solar mass black hole in 470 million years, then the standard pathway is not the only pathway. There has to be a shortcut. The standard route builds a black hole from a dead star. Star forms, star burns, star dies, black hole remains. Small seed, slow growth, Eddington limit enforced the entire time. Natarajan proposes a different route. No star, no intermediate step. A massive cloud of primordial gas, hundreds of thousands of solar masses, collapses directly into a black hole. The cloud does not fragment. It does not form stars first. It does not pass through the normal stages of stellar evolution. It just falls inward past its own Schwarzschild radius and becomes a black hole in one step. The result is a seed that is born heavy. Not 5 solar masses, not 50, 10,000, maybe 100,000. And a seed that heavy does not need to eat at the Eddington limit for billions of years to reach 10 million. It gets there in a few 100 million years, comfortably within the timeline JWST is showing us. But the conditions for direct collapse are strict. The gas cloud has to avoid fragmenting. Normally, molecular hydrogen in the cloud acts as a coolant. It radiates energy away, the gas cools, and cooler gas breaks into smaller clumps that form stars instead of one giant collapse. To prevent this, you need something to destroy the molecular hydrogen before it can do its job. One candidate is a nearby intense source of ultraviolet radiation, a neighboring galaxy or quasar that floods the cloud with photons and dissociates the hydrogen molecules. No coolant, no fragmentation, no stars, just collapse. This means direct collapse does not happen everywhere. It happens in specific environments, at specific times, under specific conditions. It is not a general mechanism, it is a narrow window. And yet, JWST is finding supermassive black holes at high redshift in numbers that suggest either this narrow window was more common than we thought, or there is yet another mechanism we have not identified. The universe built its heaviest objects first. Before the small ones had time to assemble, the giants were already running. That is not how construction is supposed to work. You do not start with the roof. The first stars burned, the first black holes formed, and together, they did something to the universe that changed it permanently. For roughly 100 million years after the Big Bang, the universe was dark. Not dark in the poetic sense, physically opaque. The gas that filled space was neutral hydrogen, atoms with their electrons still attached. Neutral hydrogen absorbs ultraviolet light. It swallows it. So even if a source of light existed somewhere in that fog, The light could not travel far. It would be absorbed within a short distance, and the universe would remain blind to itself. Astronomers call this period the cosmic dark ages. Then, the first stars and black holes switched on. They were hot. Ferociously hot. They poured ultraviolet radiation into the surrounding gas. That radiation knocked electrons off the hydrogen atoms, ionized them, cleared the fog. Each source carved a bubble of transparent space around itself. And as more sources ignited, the bubbles grew and merged. Eventually the bubbles connected, and the entire universe became transparent again. This process is called reionization, and it is the moment the universe went from blind to seeing. The models predicted that reionization should have been a slow process, a gradual brightening, like a dimmer switch being turned up over hundreds of millions of years. The first sources were supposed to be rare and weak. Not enough photons to clear the fog quickly. A long, drawn-out dawn. Brant Robertson at the University of California, Santa Cruz, and his collaborators published results in 2023 showing that JWST had found far more galaxies at high redshift than the models predicted. Enough galaxies producing enough ultraviolet photons to ionize the intergalactic medium earlier and faster than anyone had modeled. The dimmer switch was not turned up slowly. Someone flipped a breaker. The universe did not ease into transparency. It snapped into it. The Dark Ages ended faster than our physics said they could. The very first chapter of cosmic history, the part we thought would be the simplest to model because the ingredients were so basic. Pure gas, simple gravity, no complications, turns out to be the chapter we got the most wrong. The beginning was not gentle, it was abrupt. And everything that grew from that abrupt beginning, every galaxy, every cluster, every filament of the cosmic web, inherited whatever made the stars so violent. Everything we have talked about so far, every galaxy that should not exist, every black hole that grew too fast, every crack in the expansion rate, every invisible filament of dark matter, all of it sits inside a volume that we can see. And that volume is not the universe, it is our window into it. The observable universe is a sphere roughly 93 billion light years across. That number sounds large, and it is, but it is not the size of the universe. It is the size of the region from which light has had time to reach us since the Big Bang. Think of it this way. You are standing in the middle of a dense fog. You can see maybe 100 meters in every direction. Beyond that, the fog is too thick. You cannot see the rest of the field, but the field does not end at 100 meters. It keeps going. You just do not know how far. The 93 billion light-year figure is our 100 meters. Everything beyond it is there. It exists. It is real. But its light has not had 13.8 billion years to reach us yet. We are blind to it. And we will always be blind to it. Because the expansion of space is carrying it away faster than the light can close the gap. So how big is the full universe? The honest answer is that we do not know. But the models give us estimates that are difficult to process. Inflationary cosmology, the framework developed by Alan Guth at MIT in 1980 and expanded by Andre Linde at Stanford, predicts that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. During inflation, space expanded faster than light, by a factor so large that the observable universe is a vanishingly small patch of the whole. How small? Some estimates place the full universe at 10 to the 23 times larger than the observable one. That is not 23 times larger. That is a 1 followed by 23 zeros times larger. Others go further. If the inflationary period lasted slightly longer than the minimum, the ratio could be 10 to the 10 to the 10 to the 122. A number so large that writing it out would require more digits than there are atoms in the observable universe. Every anomaly JWST has detected sits inside our tiny window. Every model it has broken, every timeline it has violated, every structure it has revealed, all of it represents a fraction of reality so small that no analogy does it justice. We are not looking at the universe. We are looking at a single grain of sand on a beach that might stretch farther than the concept of distance can describe, and the grain of sand is shrinking, not because the universe is getting smaller, because the part of it we can access is getting smaller. To understand why, you have to let go of the explosion model for good. Most people carry a picture in their heads of the Big Bang as a bomb going off in empty space, matter flying outward from a central point. Galaxies as shrapnel. If that picture were correct, you could in principle build a fast enough ship, chase down any galaxy, and reach it. It would just take a long time, but that picture is wrong. There was no central point. There was no explosion into empty space. There was no empty space for the explosion to happen in. Space itself is what is expanding. Every point in the universe is moving away from every other point. Not because things are flying through space, but because the distance between them is being manufactured. Imagine baking raisin bread. You drop raisins into the dough, and as the dough rises, every raisin moves away from every other raisin. None of them are crawling through the dough. The dough between them is expanding. The farther apart two raisins are, the more dough there is between them, and the faster the gap grows. At some point, for raisins on opposite sides of the loaf, the dough is expanding faster than any signal could cross it. That is what is happening in the universe right now. The expansion rate is proportional to distance. Double the distance, double the recession speed. At roughly 14 billion light years, the recession speed equals the speed of light. Beyond that, the galaxies are receding faster than light. Not because they are violating physics, nothing is moving through space faster than light. The space itself is growing at a rate that outpaces light. JWST has photographed galaxies beyond this threshold. You can see them in the deep field images. They are real, resolved, structured. But every photon in those images is old light. It left those galaxies billions of years ago, when they were closer, when the expansion had not yet carried them past the horizon. The galaxies you are looking at have already crossed the line. Their present-day selves are in a region of space that your fastest signal will never reach. You are looking at a memory, a detailed high-resolution, scientifically valuable memory. But a memory of something that is already gone from your accessible universe. And the line is not fixed. It is moving inward. Every day, more galaxies cross it. The catalogue of reachable destinations is not growing as we get better at exploring. It is shrinking as the universe gets better at expanding. There is a boundary in the universe that works like a one-way door. Physicists call it the cosmological event horizon, and it is different from the edge of the observable universe. The observable universe is everything whose light has had time to reach you so far. The event horizon is more final. It is the boundary beyond which light that leaves today will never reach you, no matter how long you wait. Not in a million years, not in a trillion, not ever. The expansion of space between you and that point will always outpace the photons. This boundary is not a wall you can see. There is no line painted across the sky. It is a mathematical surface defined by the rate of expansion and the distance at which that rate becomes insurmountable. And it is not sitting still. It is contracting. Every second, objects that were previously inside your event horizon cross to the outside. They do not move. They do not accelerate. They just sit on their patch of space while the expansion of the intervening distance pushes them beyond the reach of anything you could ever send, see, or detect. Think of it like standing on a dock watching a boat drift away on a current. For a while, you could swim to it. The current is slow, but the current is accelerating. At some point, even if you dive in and swim as fast as physically possible, the current carries the boat away faster than you can close the distance. You watch the boat get smaller. You can still see it, but it is already gone. The universe is doing this to us continuously. The number of galaxies within our event horizon is finite and it is dropping. We are not gaining access to the cosmos. We are losing it. Every deep field image JWST takes is a snapshot of a universe that is in the process of walking away from us. The doors are closing while we are still learning how to read the room, and they are not closing slowly. The acceleration of expansion, driven by whatever dark energy is, means the rate of loss is itself increasing. We are losing the universe faster this year than we were losing it last year. There is one exception, one object that is not receding. The Andromeda Galaxy, 2.5 million light-years away, is actually moving toward us. Its local gravitational pull is strong enough to override the expansion at this distance. In about 4.5 billion years, Andromeda and the Milky Way will collide, merge, and form a single, larger galaxy. The stars will not crash into each other. The distances between individual stars are too vast, but the gravitational structures will reorganize. Our sky will change. The night will look different. Andromeda and a handful of smaller galaxies make up what is called the local group, a gravitationally bound cluster of about 80 galaxies spanning roughly 10 million light-years. Within this group, gravity wins. The expansion cannot tear it apart. These galaxies will remain accessible to each other indefinitely, but everything outside the local group is leaving, and it is not coming back. The great clusters, the filaments of the cosmic web, the billions of galaxies JWST has revealed, all of it is sliding past the event horizon on a schedule we cannot alter. Krauss and Scherer, two physicists at Vanderbilt and Case Western, published a paper in 2007 that described what this means for a civilization born in the far future. They showed that in roughly 100 billion years, every galaxy beyond the local group will have crossed the event horizon. Their light will have redshifted to nothing. No telescope, no matter how powerful, will be able to detect them. The cosmic microwave background will have stretched beyond detection. The evidence that the Big Bang ever happened will be gone. A civilization that arises in that era will look at the sky and see only the local group. They will measure the expansion and find nothing expanding. They will have no evidence that the universe was ever larger than what they can see. They will construct a cosmology that is self-consistent, internally logical, and completely wrong. They will not know what they are missing, because the universe will have erased the clues. We live in the only era when the full picture is visible. The galaxies are still detectable. The microwave background still carries its signal. The expansion is measurable. The evidence is intact. This is not a permanent condition, it is a window, and JWST is one of the instruments standing inside it, looking out while there is still something to look at. While the universe is pulling the walls back, JWST is doing something that no telescope has ever done before. It is tasting the air of other worlds. When a planet passes between its star and our line of sight, a tiny fraction of the starlight filters through the planet's atmosphere on its way to us. Different molecules in that atmosphere absorb different wavelengths. Carbon dioxide grabs one frequency, water grabs another, methane grabs a third. Each molecule leaves a fingerprint, a specific pattern of missing wavelengths in the starlight that passes through. If you can measure those missing wavelengths precisely enough, you can read the composition of an atmosphere that is hundreds of light years away without ever going there. This technique is called transit spectroscopy, and astronomers have been using it for years. But previous instruments could only detect the broadest features, the heaviest fingerprints, in the atmospheres of the largest, hottest planets. JWST changed the resolution. In July 2022, the same month that the first deep field image was released, JWST turned its spectrograph on a planet called WASP-39b. It is a gas giant, roughly the mass of Saturn, orbiting a sun-like star about 700 light-years from Earth. It is not habitable. Its surface temperature is over 800 degrees Celsius. It orbits its star in about 4 days. Nobody is living there. But the data that came back was the sharpest chemical portrait of another world ever recorded. Carbon dioxide, water vapor, sulfur dioxide, sodium, potassium, each one confirmed at high confidence. And the sulfur dioxide was a surprise. It should not have been there in those quantities. The team concluded that it was being produced by photochemistry, ultraviolet light from the star-driving chemical reactions in the upper atmosphere. Chemistry happening in real time on a planet 700 light-years away, and we could read it. This is not a detection at the edge of noise. This is a clear, unambiguous chemical inventory of a specific world. We know what the air is made of on a planet we will never visit. We crossed a line in 2022 that does not get enough attention. We went from asking whether other planets exist to reading their recipes. And the next question, the one that keeps the field awake, is whether any of those recipes include an ingredient that only life can produce. In September 2023, that question got its first serious test. Niku Madhusudan, an astronomer at the University of Cambridge, published results from JWST observations of a planet called K2-18b. It orbits a red dwarf star about 120 light-years from Earth, and it sits in the habitable zone, the range of distances where liquid water could exist on the surface. The planet itself is a sub-Neptune, bigger than Earth, smaller than Neptune, a category of world that does not exist in our solar system. We have no local example to compare it to. JWST's spectrograph found methane and carbon dioxide in the atmosphere. Both of those can be produced by geological processes, volcanic activity, chemical reactions that have nothing to do with biology. But there was something else in the data. A tentative signal, not confirmed, not at high confidence, but present in the spectrum. Dimethyl sulfide, DMS. On Earth, dimethyl sulfide is produced almost exclusively by living organisms. Marine phytoplankton, the microscopic plants that fill the surface layer of our oceans, are the primary source. They produce DMS as a byproduct of their metabolism, and it escapes into the atmosphere. It is what gives the ocean its characteristic smell. When you stand on a beach and breathe in that sharp, salty, slightly sulfurous scent, you're inhaling a molecule that was manufactured by a living cell. If DMS is confirmed on K2-18b, it would be the first detection of a molecule associated with biology in the atmosphere of a planet in the habitable zone of another star. Madhusudan proposed a model to explain the overall chemistry. A Hycean world, a planet with a global ocean beneath a thick hydrogen atmosphere. The hydrogen explains the methane. The ocean explains the DMS. The habitable zone explains the liquid water. The pieces fit, but the pieces fitting is not proof. The DMS signal is weak. It sits at the boundary of what the current data can resolve. Other teams have challenged the detection, arguing that the spectral feature could be explained by other molecules or by noise in the instrument. More observation time is needed, more transits, more photons. The answer is not in yet. What is already settled, though, is the fact that we are asking the question at this level of specificity. We are not debating whether habitable planets might exist somewhere in the abstract. We are arguing about the concentration of a specific molecule in the atmosphere of a specific planet at a specific distance, measured by a specific instrument. The resolution of the question has changed permanently, and the next set of observations could close it. There was one system that carried more hope than any other, TRAPPIST-1, a red dwarf star about 40 light-years from Earth, small and cool, roughly the size of Jupiter. In 2017, astronomers confirmed that it had 7 rocky planets, all of them roughly Earth-sized, 3 of them sitting in the habitable zone, 7 chances, 3 good ones. The geometry was perfect for transit spectroscopy. The star was small, which meant the planets blocked a larger fraction of its light, which meant the atmospheric signal was stronger. If there was a place where JWST could find a second Earth, this was it. The first results came back in 2023. Lustig, Jager, Green, and their collaborators published the JWST observations of TRAPPIST-1b and TRAPPIST-1c, the 2 planets closest to the star. The data was clean, the signal was clear, and the answer was blunt. No thick atmosphere detected on either planet. Not carbon dioxide, not oxygen, not nitrogen. The thermal emission measurements were consistent with bare rock. airless worlds baking under a star that sits close enough to fill half the sky. The likely culprit is the star itself. Red dwarfs are not gentle. They are prone to violent flares, bursts of high-energy radiation that can be thousands of times more intense than anything the sun produces. For a planet orbiting close to a red dwarf, these flares are not occasional storms. They are a continuous bombardment. Over hundreds of millions of years, the radiation strips the atmosphere molecule by molecule. It does not matter how thick the atmosphere was at the start. The star sandblasts it away. This is not a problem unique to TRAPPIST-1. Red dwarfs make up roughly 70% of all stars in the Milky Way. They are the most common type of star in the galaxy, and their habitable zones are close in, precisely where the flare damage is worst. If red dwarfs reliably strip the atmospheres of their habitable zone planets, then 70% of the galaxy's real estate just got crossed off the list. The universe builds planets the right size, puts them the right distance from their star, gives them the right ingredients, and then erases the result. It sets the table and then flips it. Before JWST, there was a lesson about what happens when you announce a biosignature too early. In September 2020, Jane Greaves and her team at Cardiff University published a paper claiming the detection of phosphine in the atmosphere of Venus. On Earth, phosphine is produced by anaerobic bacteria, microorganisms that live in environments without oxygen. No known geological or chemical process on a rocky planet can produce phosphine in the quantities Greaves reported. The implication was immediate and global. Life on Venus. Headlines everywhere. Then the data was reanalyzed. Other teams could not reproduce the signal. The spectral feature that Greaves identified was at a frequency shared by sulfur dioxide, a molecule that is abundant in Venus's atmosphere and has nothing to do with biology. The detection method relied on subtracting a baseline from the spectrum, and small errors in that subtraction could produce phantom signals. Within a year, the consensus had shifted. The phosphine was probably not there. The signal was likely an artifact of data processing. Sarah Seeger, a planetary scientist at MIT who has spent her career developing the theoretical framework for atmospheric biosignatures, drew a clear lesson from the Venus episode. One molecule is not proof. A biosignature is not a single detection. It is a context. You need to know what gases are present together, what their ratios are, whether there is an abiotic pathway that could produce the same combination, and whether the detection is reproducible across multiple observations. Biology is a diagnosis of exclusion. You identify it by ruling out everything else first. This framework is what makes the K2-18b result both exciting and provisional. DMS fits the biological pattern, but only if it survives further scrutiny, only if the signal holds across additional transits, and only if no abiotic explanation emerges. JWST gives us the data. But data is not an answer. Data is a question asked with more precision than we could manage before, and the question of whether we are alone in this universe remains unanswered. Not because we lack the tools, we have the tools now, but because the answer requires time, repetition, and patience that the universe is not obligated to grant us. We have spent this entire time looking outward, at galaxies that should not exist, at an expansion rate that does not balance, at a dark architecture we cannot see, at the chemical breath of alien worlds. But there is a direction we have not looked yet, forward, into time. And the view forward is where the universe reveals what it actually is, a machine with a timer. Stars are not permanent. They are fires. They burn fuel, and when the fuel runs out, they die. The most massive stars burn brightest and die fastest in a few million years. Medium stars like the Sun last about 10 billion. The smallest red dwarfs, the ones that sip their hydrogen so slowly they barely glow, can last up to 10 trillion years. That upper limit, the lifespan of the longest-lived stars, defines what Fred Adams and Greg Laughlin, two astrophysicists at the University of Michigan, called the stelliferous era, the age of stars. It began roughly 150 million years after the Big Bang, when the first nuclear fires ignited, and it will end when the last red dwarf exhausts its fuel, somewhere around 100 trillion years from now. The universe is currently 13.8 billion years old. That means we have lived through roughly 1/10,000th of the stelliferous era. 1/10,000th. If you compress the entire age of stars into a single 24-hour day, the current moment falls in the first 8 seconds after midnight. Not the first hour, not the first minute, the first 8 seconds. Every human civilization, every empire, every war, every discovery, every song, every life that has ever been lived on this planet, all of it happened in the first 8 seconds of a day that will last until the following midnight. We are not in the middle of the story. We are so close to the beginning that the beginning has not had time to finish introducing itself. And every anomaly JWST has found, every impossible galaxy, every broken model, every invisible structure, all of it comes from data collected in those first 8 seconds. We are trying to understand a 24-hour machine by looking at the first 8 seconds of its output. And after the 24-hour day ends, there is no tomorrow. When the last red dwarf burns out, the universe does not restart. There is no new generation of stars waiting to take over. Star formation requires dense clouds of cold gas, and by that point, the gas will have been used up, blown away, or diluted by expansion to the point where gravity cannot pull it together. The raw material for stars will be gone. What remains is a universe of corpses. White dwarfs, the dense remnants of dead sun-like stars, will slowly cool over trillions of years, dimming from white to yellow, to red, to infrared, to nothing. They will become black dwarfs, objects so cold they emit no detectable radiation. Neutron stars will spin down and go silent, and the supermassive black holes at the centers of dead galaxies will sit in the dark, slowly evaporating. That evaporation is real. Stephen Hawking showed in 1974 that black holes are not truly black. Quantum effects at the event horizon cause them to radiate particles at an extraordinarily slow rate. For a supermassive black hole, this process takes an almost incomprehensible amount of time. A black hole with the mass of the one at the center of the Milky Way would take roughly 10 to the power of 87 years to evaporate. That is a number with 87 digits, but it is finite. Even the most massive black holes in the universe, the ones that weigh billions of solar masses, will eventually evaporate. Nothing is permanent. Below that timescale, there may be an even deeper decay. The proton, one of the building blocks of every atom, may not be stable forever. Grand unified theories of particle physics predict that protons decay with a half-life somewhere above 10 to the 34 years. If that is true, then over unimaginable stretches of time, the atoms themselves will fall apart. Iron, the most stable nucleus, will eventually disintegrate. Matter, the physical substrate of everything, will dissolve into a thin soup of leptons and photons at a temperature approaching absolute zero. This is heat death. Not an explosion, not a collapse. A slow, irreversible slide into maximum entropy, a state where energy is distributed so uniformly that no work can be done, no information can be processed, no structure can exist. Time continues, but nothing happens. The difference between one moment and the next vanishes. The universe does not end. It simply becomes indistinguishable from nothing. Heat death is the slow ending. But there is another possibility, and it is not slow. In 2003, Robert Caldwell at Dartmouth College published a paper describing a scenario in which dark energy does not remain constant and does not weaken. It strengthens. The parameter that governs the behavior of dark energy is labeled W. If W equals -1, dark energy is a cosmological constant, steady, unchanging. The expansion accelerates at a fixed rate and the universe dies cold. But if W drops below -1, into a regime physicists call phantom energy, the expansion does not just accelerate, it runs away. At first, the effect is subtle. The expansion pulls galaxy clusters apart. Clusters that were gravitationally bound to each other lose their grip. The filaments of the cosmic web stretch and snap. Then it gets closer. Individual galaxies begin to unbind. The gravitational force holding the Milky Way together is overcome by the stretching of the space within it. Stars drift apart. Then the solar system. The expansion rips planets from their orbits. Then it reaches the scale of matter itself. Molecules are torn apart. Atoms are torn apart. The electromagnetic force that holds electrons to nuclei is overwhelmed. Nuclei break. Protons and neutrons scatter. The fabric of matter dissolves from the top down, from clusters to atoms, in a cascade that ends when there is nothing left to tear. This is the Big Rip. And it does not take trillions of years. Depending on the value of W, it could happen in as little as 22 billion years from now. That is less than twice the current age of the universe. The DESI results from 2024 do not confirm phantom energy, but they do not rule it out. The data shows a mild preference for dark energy that changes over time. If that change is in the direction of strengthening rather than weakening, the Big Rip moves from theoretical exercise to plausible forecast. Two possible endings. One is silence, the other is a tear. In neither of them does anything survive. And we do not currently have the data to tell which one is real. Two endings, both terminal, a slow freeze or a fast tear. And in between those two futures, here we are, awake, aware, asking questions. But our presence in this particular moment is itself a data point that requires explanation. Life based on carbon chemistry needs a specific set of conditions. Stars have to be burning because stars forge the heavy elements. Those elements have to have been scattered into gas clouds by supernovae, so that second-generation stars and rocky planets can form. The expansion rate has to be in a corridor that allows gravity to build structures without everything flying apart too fast. The background temperature has to be low enough for complex chemistry, but high enough for liquid water. The window is narrow, and JWST is making it narrower. Every observation that pushes galaxies earlier in time means the initial conditions had to be more precise. Every atmosphere stripped by a red dwarf means stable environments are rarer than we assumed. Every crack in the expansion rate means the mechanism governing the corridor is less stable than we modeled. The window we occupy is not a comfortable middle ground. It is a ledge. The conditions that allow you to exist are not typical. They are not the default state of the universe. They are a brief alignment of parameters, a gap in the timeline where the temperature is right, the chemistry is available, the expansion is cooperative, and the stars are still burning. Before this window, the universe was too hot and too young. After this window, it will be too cold and too dead. We are standing in the crack between two kinds of darkness, and the crack is not as wide as we thought it was. The question that follows is the one that physicists find hardest to answer. Why is the crack exactly this wide? Why are the parameters set to the values that allow it to exist at all? The cosmological constant lambda is set to a value of approximately 10 to the negative 120 in natural units. To feel what that number means, try this. Write down a decimal point, then write 119 zeros, then write a 1. That is the precision. If lambda were a fraction larger, the expansion of the universe would have outrun gravity before matter had time to clump. No clumps means no galaxies. No galaxies means no stars. No stars means no heavy elements. No heavy elements means no planets, no water, no carbon, no amino acids, no cells, no you. If lambda were a fraction smaller, gravity would have won. The expansion would have stalled and reversed. The universe would have collapsed back into a singularity within a few million years. A breath, then nothing. Now look at the strong nuclear force. This is the force that holds the core of every atom together. Protons carry a positive charge. Positive charges repel each other. In any nucleus heavier than hydrogen, something has to override that repulsion and lock the protons together. That something is the strong force, and it operates at extremely short range, roughly the diameter of a proton. Change its strength by 0.5% and a very specific process inside stars breaks down. When 3 helium nuclei collide inside a stellar core, they can fuse into carbon, but only because of an energy resonance, a precise match between the energy levels of helium-4 and the excited state of carbon-12. Fred Hoyle predicted this resonance in 1953, reasoning backward from the fact that carbon exists. The resonance was found exactly where he said it would be, but it depends on the strong force being exactly the strength it is. 0.5% off, and the resonance vanishes. Carbon does not form. Without carbon, there is no organic chemistry. Without organic chemistry, there is no biology. Steven Weinberg, in 1987, used the requirement that galaxies must form to calculate an upper limit for the cosmological constant. His prediction, made before the value was measured, turned out to be correct, and JWST has been tightening the constraints since. Every impossible early galaxy means the initial density fluctuations had to be calibrated even more precisely than the models assumed. Not just the constants, the starting conditions. Precision layered on precision, with no explanation for why any of it is set to the values it holds. There are 2 explanations on the table, and neither one leaves you standing on solid ground. The first is the multiverse. In 2003, Leonard Susskind at Stanford and Raphael Bousso at Berkeley formalized an idea that had been circling theoretical physics for years. The equations of string theory do not produce a single solution. They produce a landscape of solutions, roughly 10 to the 500 possible configurations of physical law. Each configuration corresponds to a different vacuum state, a different set of constants, a different version of physics. 10 to the 500 is not a number you can visualize. It is more than the number of atoms in the observable universe, raised to the power of itself several times over. Andre Linde at Stanford and Alexander Vilenkin at Tufts had already provided the mechanism. Eternal inflation. The inflationary field that drove the expansion of the early universe does not stop everywhere at once. It stops in patches. Each patch becomes a bubble, a pocket universe with its own vacuum state, its own constants, its own laws. The bubbles keep forming, endlessly, in an inflating background that never stops. Every one of the 10 to the 500 vacua is realized somewhere. Every combination of constants exists in some bubble. In this picture, fine-tuning is not a mystery, it is a selection effect. We observe the constants we observe because we can only exist in a bubble where the constants allow observers. The other bubbles, the ones where lambda is too large or the strong force is too weak, are real, but they are empty. No one is there to measure them. This explanation is logically consistent, mathematically elegant, and completely untestable. We cannot see other bubbles. We cannot detect them. We cannot send a signal or receive one. The multiverse, if it exists, is permanently beyond our event horizon. It is an answer that resolves the question while removing it from the domain of science entirely. It is philosophy expressed in equations, which does not make it wrong, but it does mean we cannot know if it is right. The second explanation goes in a different direction. In 2003, the same year Susskind published the landscape paper, Nick Bostrom, a philosopher at Oxford, published a paper that has refused to go away. Bostrom's argument is not about physics, it is about statistics. He starts with a simple premise. If a civilization reaches a level of technological maturity where it can simulate conscious beings in a computed environment, and if such civilizations choose to run such simulations, then the number of simulated minds in the universe will vastly outnumber the biological ones. And if you are a mind that cannot tell whether it is simulated or biological, the odds favor you being simulated. This is not speculation dressed as science fiction. It is a formal trilemma with 3 branches. Either civilizations almost always go extinct before reaching simulation capability, or they reach it and choose not to run simulations, or we are almost certainly inside one. Each branch is falsifiable in principle. None has been falsified in practice. In the context of fine-tuning, the simulation hypothesis reframes the problem entirely. The constants are not fine-tuned by luck or by a multiverse. They are parameters entered into a system. The precision of lambda, the resonance of carbon-12, the strength of gravity, all of it is input, not output. Like the settings of a physics engine in a video game. Somebody chose them. Somebody typed the values. The universe does not need to explain its own calibration because the calibration came from outside. Two answers to the same question. The multiverse says, you are a statistical accident in an infinite ocean of failed experiments. The simulation says, you are a product of deliberate construction in a system designed by something else. In neither case are you at the center. In neither case are the constants set for your benefit. In both cases, the reality you inhabit is contingent, dependent on conditions you did not choose, cannot change, and may not fully understand. The ground under your feet is real enough to stand on, but the reason it is there has nothing to do with you. Every generation of astronomers believed they had finally measured the size of the house they lived in. And every generation was wrong. Claudius Ptolemy placed the Earth at the center of everything. The stars were fixed on a sphere just beyond Saturn. The universe was small, tidy, and built around us. Copernicus removed the Earth from the center and put the sun there instead, but the universe was still the solar system. It was bigger, but still comprehensible. Then William Herschel mapped the Milky Way and showed that the sun was one star among billions, off to one side, not even in a particularly interesting neighborhood. The universe grew again. Then Edwin Hubble, in 1924, proved that the Milky Way was not the universe. It was one galaxy among billions, and those billions were flying apart. The universe was expanding, possibly infinite, and we were nowhere near the center of any of it. Each correction carried the same message. You are smaller than you thought. You are less central than you assumed. The universe does not revolve around you, and it was not built with you in mind. JWST delivered the final correction. We are not just off-center. We cannot see most of what exists. We are standing on 5% of the material in the first 8 seconds of a trillion-year day, inside a window that is closing, surrounded by architecture we cannot detect, governed by forces we cannot explain, tuned by constants we cannot account for. Every previous generation at least had the comfort of thinking they could see the whole picture. JWST took that away. We now know that most of reality is not just unknown to us, it is unknowable. It operates beyond the horizon that light can cross in the remaining lifetime of the universe. We will never see it, and it will never know we were here. On February 14th, 1990, the Voyager 1 spacecraft, at a distance of roughly 6 billion kilometers from Earth, turned its camera around and took a photograph. The image showed a pale blue dot, less than a single pixel across, suspended in a beam of scattered sunlight. Carl Sagan had requested the picture. He wanted to see what Earth looked like from the edge of the solar system. The answer was almost nothing. A speck. A crumb of light in an ocean of black. Sagan spent the rest of his life talking about what that image meant. Every person who has ever lived, every government, every religion, every war, every act of kindness, every birth and every death, all of it happened on that crumb. The entirety of human experience, on a dot that a passing alien could miss without trying. That was 1990. Sagan was looking at our position in the solar system. He did not have the data that JWST has now provided. He knew the universe was large, he knew we were small, but he did not know the details we now know. He did not know that our models of galaxy formation were wrong. He did not know that the expansion rate was broken. He did not know that 95% of the universe was invisible architecture. He did not know that the constants were tuned to a precision that has no explanation. He did not know that the window of time in which life is possible might be a statistical crack between two eternities of silence. Sagan showed us how small the dot was. JWST showed us what the dot is floating in. And what the dot is floating in is a machine that was running before the dot existed, that will keep running long after the dot is gone, and that was never, at any point, designed for the benefit of anything living on its surface. Before JWST, we had the option of not knowing. That option is gone. Previous generations could look at the night sky and see beauty without discomfort. The stars were distant and decorative. The gaps between them were empty in a way that felt peaceful. The silence of space was interpreted as calm, not as data. The absence of signals from other civilizations could be explained by the absence of other civilizations, and that explanation felt tidy and sufficient. The models worked. The timeline made sense. The expansion was a known quantity with a known outcome. We were small, yes, but the smallness was manageable because the picture was complete. JWST broke the completeness. The models do not work. The timeline does not make sense. The expansion might be a variable. The silence persists despite confirmed conditions for life. The architecture of reality is invisible and structured in ways we cannot account for. The initial conditions were calibrated to a degree that suggests either an infinite ensemble of universes we can never access, or a constructed system whose constructor we can never identify. The picture is not complete, it is fractured. And we are the first generation of humans to hold every piece of the fracture at once. This is not a burden that comes with instructions. There is no protocol for discovering that your map of reality has been drawn on 5% of the available surface. There is no manual for learning that the remaining 95% has its own architecture and its own rules, and does not require your awareness to function. But the knowledge is here. It arrived in data packets from a machine sitting 1 million miles away in permanent shadow, and it does not expire, and it does not soften, and it does not come with an opt-out clause. We are the generation that looked and the generation that cannot unlook, and underneath all of it, there is the silence. We have confirmed that the conditions for life are not rare. The chemistry is there. The planets are there. The habitable zones exist. The building blocks, carbon, water, energy, are scattered across billions of systems in the observable universe alone. JWST has verified the ingredients at a level of specificity that was impossible 5 years ago. We know the recipe is common, and nothing is answering. Before JWST, the silence could be explained by ignorance. Maybe habitable planets were rare. Maybe the chemistry was wrong. Maybe life requires conditions so specific that Earth is the only place where they converge. Each of those explanations reduce the paradox by reducing the denominator. Fewer eligible planets means fewer chances for life, which means less reason to expect a signal. JWST removed those explanations. The denominator is large, the conditions are widespread, the chemistry is confirmed, the habitable zones are real, the planets exist in the billions, and the silence remains absolute. Not because we have not listened. We have been listening for over 60 years. Not because our equipment is poor. JWST is the most sensitive instrument ever built. The silence after JWST is qualitatively different from the silence before it. It is silence against a background of confirmed opportunity. It is the silence of a phone that should be ringing and is not. That silence is not an absence of information. It is information. It is the heaviest data point in the entire dataset. Every model of the universe, every theory of life, every assumption about intelligence and expansion and survival has to account for it. And none of them do. Not fully. Not satisfactorily. The universe built the stage, lit the lights, tuned the instruments, and the theatre is empty. We are sitting in the front row, and the only sound is our own breathing. We built an eye that sees the beginning of time. It works better than we designed it to. And the first thing it showed us was that our models were wrong. We found galaxies that assembled before the assembly line existed. We found black holes that outgrew their own speed limit. We found an expansion rate that two independent methods cannot agree on. We mapped the shadow of an invisible architecture that holds everything together and accounts for 95% of what is real. We watched the first light of the universe ignite faster and harder than any simulation predicted. We measured the distance to objects we have already lost forever. We tasted the air of alien worlds and found the chemistry of life in places we cannot reach. We calculated the lifespan of the stars and discovered we are standing in the first 8 seconds of a day that will last 100 trillion years. We looked at the numbers holding reality together and found them set to values so precise that no theory of randomness can explain them. We considered the alternatives, an infinity of unseen universes or a constructed simulation, and found that both answers remove us from the center of the story. And through all of it, across all those billions of light years and billions of years, the universe said nothing back. Everything we covered today pushes in one direction, down. The scale pushes down. The isolation pushes down. The broken models push down. The precision of the constants pushes down. The silence pushes down. If you add it all up, the conclusion seems obvious. We are small, we are brief, we are probably alone, and the machine we live inside was not built for us. But here is the thing that gets lost in the math. You are still here. You sat through all of this. You heard numbers that most people will never encounter. You followed a thread that started with a gold mirror in permanent shadow and ended with the question of whether reality itself was designed. You did not look away. That matters more than it sounds like it should. The universe did not have to produce you. There is no law of physics that requires a nervous system capable of understanding the cosmological constant. No equation demanded that a species on a small rocky planet would build a telescope, park it 1,000,000 miles from home, and use it to photograph the moment the first stars caught fire. None of that was required. And yet here you are, doing exactly that. The only place in the known universe where the universe is being understood is inside your head. That is not a comforting thought. It is not meant to be. It is a fact. And it carries weight. You are the universe looking at itself and knowing what it sees. That has happened here and, as far as we can tell, nowhere else. Not in any signal we have received, not on any planet we have tested, not in any data that has come back from any instrument ever built. Whatever this strange, hostile, precisely calibrated, overwhelmingly silent reality turns out to be, you are the part of it that noticed. And tonight, from wherever you are, the same sky that JWST is scanning right now is above your head. The same photons, the same ancient light. It has been traveling for billions of years, and it ended its journey here, on you, on the one thing in the cosmos that can look back and say, I know what you are. Thank you for being here to hear this.